Welcome to Protocols. In this chapter, we'll be looking at the OSI model, TCP/IP, ICMP, UDP, ARP, DNS, SSH, SNMP, and SMTP. The top layer is the application layer of the OSI model. It's a 7-layer model. This layer is the closest to the user. When you think of this layer, those protocols of this layer allow the applications to communicate to applications on remote systems. You can also think of it as interacting with applications that we run on the PCs. Don't think of them as the actual applications like Microsoft Word or Excel, but think of them as interacting with those applications. Some protocols at this layer: SMTP, HTTP, LPD, think Linux, Telnet, and TFTP. Next layer down, layer 6, is a presentation layer. No protocols work at this layer, only services. At this layer, we're thinking of conversion. We're thinking of standardized formats, conversions between different graphics formats, possibly different sound formats, just different systems of conversion. GIF, ASCII, Unicode, JPEG, TIFF. Other functions that take place at this layer, you think of encryption, also decryption, compression, and the opposite, decompression. Session layer. At the session layer, we could imagine a phone call occurring, and you make the phone call, you actually dial, you say hello, you do your communication, you have dialogue, and then you say goodbye and hang up. Essentially, dialogue management between the programs. Access control, recovery, and synchronization. As the phone call analogy, we look at the setup of the call, the maintenance, the teardown of the session. We've basically had a communication session when we've made a phone call. At this layer, we can also think of how the conversation occurred, whether we were allowed to have full duplex or half duplex. With full duplex, think of being a telephone again, being able to talk at the same time, not that you hear each other, but being able to talk on both ends of a phone call. We have two-way conversation at the same time, versus half duplex, only one application can communicate at a time. Somewhat reminds me of like CB radio. You know, you speak and you say over, and then the other person speaks, and then they say over, one at a time. Protocols that you could associate with the session layer: SQL, NFS, and RPC. Transport layer. I imagine reliability when I think of the transport layer. Two popular protocols, especially at the very bottom of the slide, is TCP and UDP. But I mostly think of TCP. A lot of what we do is TCP based. When you think of the transport layer, it's end-to-end packet transfer using connection-oriented or even connectionless protocols. It's not always perfectly reliable because we do have a protocol called UDP, and UDP is actually going to be connectionless. Transport protocols are concerned with getting data from one system to another. It's not all the way at the application to application, like application layer. It's not communications up quite that high. Many application layer protocols that we use will tie into a transport layer protocol such as TCP or UDP. And that's a pretty good picture on the slide. As you can see, they've got Office and Outlook and Internet Explorer at the top, but yet all of those tie into the transport layer, assembly data into a stream. Also at this layer, we are segmenting the appropriate size of packets for the processing by the network layer, because what we're transmitting may not be the right size, so that has to be segmented. The protocols, again, that you would know more of would be UDP and TCP, because these both are within the TCP/IP protocol suite. SPX was an old Novell protocol that would be kind of comparable to TCP. When I think of the network layer, my mind, just like the slide says, routing. I think of routers. I think of just basic routing of packets. Think of IP addressing in modern day. So addressing takes place at this layer. We look at routing protocols at this layer. Anybody who studies a class on Cisco routers would be spending much time at the network layer in their discussion. When a packet is sent down from the transport layer, the network layer protocol adds the address and creates a network header. As we go through the OSI model, information is passed down from the top at the application layer, and as it goes down through the layers, there's always additional information being added. Think of it as addressing information, telling the packet where to go. We also associate data at the network layer as being called a packet. We can add security to this information through a protocol called IPsec, IP security. So confidentiality, authentication, and integrity is basically added to what you have at the network layer through the IPsec. Very commonly used with virtual private networks, VPNs. So you'll hear people talk about, actually you'll hear it later, but L2TP, Layer 2 Tunneling Protocol with IPsec. Some protocols that work at this layer: IP, RIP, ICMP, IGMP, IGRP, and BGP. Then when you move down to the data link layer, Layer 2, at this layer, equipment-wise, not so much discussed here, but equipment-wise, I think of a switch, like a Cisco switch, for example. And they say the sender breaks down data into frames and transmits sequentially. Technologies you could think of here would be, we used to have token ring. Ethernet's quite common now, and as well as ATM. And when we think of the data at this level, a lot of times we'll use words like frame or framing. These days, we use media access at this layer, and it's carrier sense multiple access with collision detection, but CSMA. There's also polling. You can imagine that might be a mainframe environment. We could also look at an older technology of media access at this layer called token passing, if you can imagine token ring. Has synchronization and error control. When you break the data link layer down into sublayers, we have the 802.2 and the 802.3. As you can see in the picture, the 802.2 is the closest to the network layer, which is the logical link control. And at this layer, information can be passed up to, when we're going the other direction, up to the network layer, interacting with LLC, logical link control. And at that layer, it would identify whether we were talking IP or, in the old days, IPX for Novell. And the 802.3, we start thinking more of a technology, the media access control layer, MAC layer. We could associate that with Ethernet. There's other ones like 802.11, think wireless. 802.5 was the token ring. Again, token ring has lost popularity due to Ethernet being superior to it. We've got everything faster. But the data link layer, again, think switches. Switches are quite consumed with what is your MAC address. They learn the MAC address. That's a physical address of your network card. And that is at this data link layer. And that was the big, great thing about switches when they came out over the existing hub devices that we had, is there was finally a MAC address awareness in the device. So when you wanted to communicate with another device, you would actually just look at a table that the switch would have, and it would have the MAC addresses in there once they were learned. That would spell out what PC was connected to what port on the actual physical switch. This occurs, again, at the data link layer. Physical layer. When it really comes down to these bottom layers especially, physical layer, for example, layer 1, if everything's not correct at the physical layer, it's not going to work at a higher layer. And when you think of the physical layer, you could simply think of even cabling and the connectors. And if you've got the wrong type of network cable, the wrong types of connectors, or the cabling is bad, you're not going to get anywhere. So you're thinking bits, 0 and 1. And with bits, bits are turned into voltage. So encoding a voltage binary representation varies between your different technologies. You've got your local area network, your metropolitan area network, and your wide area network technologies, and there's some definite differences there. And this does provide standards for the different interfaces to the different media that we have. And there's going to be some differences as well with the electrical signaling and the format. And there's also wireless. We use radio frequencies for wireless. We're not using what some books may call bound media, basically cable. With wireless, it's like in the airwaves. It's just out there in the air. We can't really see it. But again, the physical layer, if everything is not correct, you've got the wrong type of cabling plugged into your existing cabling, nothing's going to work well above that, if at all. So there's definitely a dependency from the layer 1, which is a physical layer, all the way up to layer 7, the application layer. Now, thinking of the protocols, here's your layers. Again, physical, all the way up to application. Layer 1's at the bottom. Layer 7 is at the top. It's kind of nice to see some of the more interesting protocols here. If we were to start at the bottom, I'll just pick out some of the more interesting ones. Physical layer, you're thinking of connectors. And a lot of what you're seeing here is really wide area network connectivity that they're showing here, like the EIA TIA 232. And you think of that as, some of us will go around saying RS-232 or serial. So these are some of the varieties of serial connections, but there's many more beyond that. And then at the data link layer, we used to have SLIP, but that was replaced by point-to-point protocol. And at the data link layer, again, there's a MAC address awareness. There's an understanding of what is your MAC address. Many protocols will depend on PPP, point-to-point protocol. Even back in the dial-up days, we were using PPP, and we still do. I'm not going to go through every single one of these, but of interest, there's ARP, Address Resolution Protocol. That's a really nice one to be able to translate your MAC address. Looking at trying to understand what machine, what MAC address, and of course that table. I'm going to try to show you that. Okay. Like this is an ARP table. You can actually see what IP, which is layer 3, what IP address goes with what physical address. Okay, and the ARP table can be corrupted, due to hacking and hackers, but normally we trust it. Your computer relies on it. Reverse ARP would actually just be the opposite direction, but normally you're thinking, I know my IP, I need the MAC address, and that's what's usually happening with ARP. If I want to interact with this 192.168.1.4 device, then my computer will check its ARP table and say, oh, that's the physical machine I need to go to. And that's kind of the nature of ARP. I know the IP, I need the MAC. Reverse ARP just goes, I know the MAC, I need the IP. L2TP, I mentioned that one. That's another interesting one. L2TP, Layer 2 Tolling Protocol. I think of that as being used with virtual private networks and incorporated with IPsec to give you security at the network layer. The network layer is layer 3. With that, some primary protocols. These days we use IP. And when you ping a device, the messages that you get back to let you know, echo reply, that the device is there, you are relying on a protocol called ICMP, Internet Control Message Protocol. Many times, though, ICMP is being blocked at the router. They're actually router / more so firewall. Routers can have firewalls in them, and that's because people who kind of gotten tired of denial of service attacks, so they try to block the ICMP, which would help the hacker, of course, know that you're there and see the connectivity, and so it's blocked many times. RIP is a routing protocol, very basic one. IPX, just realize that's a much older protocol you most likely won't run into for Novell. Transport layer. When you think of the transport, since we live in a TCP/IP world, I would say just TCP/UDP would be of great interest. TCP gives you the reliability. Certain protocols at the application layer that need the reliability, need the confirmation back and forth, that we have a reliable connection, like I send you some information and you come back and say, yes, I got it, that's TCP. If I just send you information and it's a best effort delivery, maybe like sending a postcard, I hope you got it, that would be UDP based. Some things we do application layer wise, maybe like video streaming, we would want to just send the information and we don't need a confirmation back so much. It would be a cyclic redundancy check, but that would be it. But it'd be much quicker to not have to confirm and always say, here it is, did you get it? Yes. Here it is, did you get it? Yes. That's TCP. UDP is like, here it is, I hope you got it. We'll do a little check to make sure everything went well, but it won't be perfectly reliable. Secure Sockets Layer, SSL. You see that used for secure websites, and you'll see it represented as HTTPS, by the way. SPX, again, that's Novell. I'm not putting down Novell, but Novell of today is not using that anyway. That was, gosh, mid-90s and a little bit later, so pretty old. Session layer, remember that was like having a communication session compared to a phone call. Popular protocols, Microsoft has always had NetBIOS built into it. There's NFS more on the Linux side. SQL, remote procedure calls, RPC. Presentation, remember that one was conversion between different formats. It was compression, decompression, a lot of different format differences between, again, different graphic formats, different sound formats, ASCII, EBCDIC. Application layer, that's layer 7. When you think of this layer, very popular protocols. I'll just do the best ones. DNS, domain name system. When we go out to the World Wide Web, we type in www.microsoft.com. We expect that to be resolved, and that's due to DNS. FTP, File Transfer Protocol, extremely popular for transferring information. If you haven't heard of TFTP, it's like a lightweight FTP. Let's see, SNMP is a big one, Simple Network Management Protocol. And with that one, we think of network management, managing devices. Another interesting one, basically Simple Mail Transfer Protocol. Think of email. Telnet, people who use Cisco routers and need to remote into the Cisco routers would use Telnet. And HTTP, like any website you go to that's not secured, and that's application. So the OSI model is a 7-layer model. If you were to say what is layer 8, a lot of people would tell you the user, because that's where we interact. And with these layers is a layer 8, which is not an official layer. Okay. Now, some of this will be just going more into some of the more interesting ones. The TCP/IP protocol suite is the most common one we see now. It was named after 2 popular protocols from the suite, just TCP and IP. TCP is connection-oriented transport layer protocol, and we saw that at the transport layer. And as you can see, the IP is at the network layer, and that's connectionless because it would be faster that way. And we don't always know from start to finish where we're going to, what path we will take to get there. Just like if you drive to the mall, you have a place you want to go and you run into a traffic jam, you will alter your way to get to the mall, and so does IP. So it is a suite of protocols we use that govern how data travels over a network. We've used many protocols before this, but TCP/IP seems to be the one that will work with a variety of computer types, and I think it's here to stay. When you study TCP/IP, there are port numbers that are mapped to protocols. So people that do firewalls will many times have to, if they want to allow or disallow a port or a certain protocol to come through the firewall, we would need to know the port number. And here's some of the popular ones that are worth knowing. And of course, well-known ports are from 0 to 1023. And FTP, 20 and 21, both ports are used. Simple Mail Transfer Protocol, that's email. Port 25, maybe you've used a product like Cisco Works or HP OpenView, that would use SNMP, Simple Network Management Protocol to manage devices, port 161. HTTP, just surfing the internet. And Telnet may not be as common to you, but if you remote into a router, you would use Telnet, or maybe an older Unix system. And where it's coming from, the source port, is usually a high dynamic number, while the destination would generally be one of these well-known port numbers under 1024, like FTP or HTTP or something like that. So TCP and UDP use ports to communicate with upper layer protocols. That's a pretty nice picture. It shows you the things we would do, like the web browsing with Internet Explorer, using an email client, ping activities, secure shell, which is like a replacement to Telnet but more secured. You can also see in this picture how TCP and UDP are separated. With this, you can see like Telnet and simple mail transfer protocol, domain name system, DNS, HTTP, web surfing, POP, usually POP3 for email. These are all needing the extra reliability, which would slow things down, but there would be more verification between the sender and the receiver to make sure there's no errors. TCP tends to be more reliable. UDP-based applications, as you can see listed there, they've got FTP, DNS, it's doing a couple of them, simple network management protocol. These have more of, I guess, a need for speed. They don't need quite as much back and forth reliability checks. So with this, they can get away with UDP and therefore it's faster. It can be faster. So more on this. You saw that with several of the protocols were TCP and the others were UDP. And with this, the ones that need to be connection oriented and need to be more reliable, and they perform a handshake, have error detection, can correct errors, can adjust how much information is sent to the recipient at a time. It's like a window size. This is all TCP oriented. TCP reminds me sometimes of making a phone call and the ability to say to the person you're talking to, hey, I didn't hear that, especially on a cell phone. Could you say that again? I didn't catch what you just said to me. Well, with that, that's TCP with the error detection and correction. And it's doing this with data. And UDP, that ability does not exist. It's connectionless. It's still useful, but yet unreliable. There's no back and forth handshake. It's just like, here it is, I hope you got it. Postcard again. And as you can see in the drawing on the right between the client and the server, this is called a TCP three-way handshake. It's basically saying to this client to server, hi, I want to initiate this connection, so here's synchronize. And then the server is going to come back and say synchronize to you and acknowledge your request. And then finally, we say acknowledge to the server. And that completes the connection. This is called the three-way handshake. Now, ARP, another good protocol, very necessary protocol. I showed you that from the command prompt, where you could see the IP address and the actual MAC address mappings. So that's what it does. It maps the IP address to the MAC address. And these days, we're still using 32-bit numbers, and we're thinking, if you take it down to binary, it's 32 bits, okay? And as far as the MAC address, it's 48-bit if you look at it from that perspective. Although the MAC address is generally viewed not in bits, but in hexadecimal. But essentially, I'm going to back out just to show that to you again, because I still have it there. This is your ARP table. IP addresses of other computers, MAC addresses. It is presented in hexadecimal, as you can see. Most of these are dynamically learned. So when my PC needs to talk to one of these guys, .10, .11, .12, it is able to figure out what physical machine it goes to. If I need to talk to .5, which is not in here, it's going to have to send out a broadcast and try to find that system, which is going to create more traffic. So when you think of the data link layer, which was layer 2, it understands MAC addresses. It really doesn't comprehend IP addresses. You have to get to layer 3, which is the network layer, to comprehend that. So many things we do rely on ARP. And if we're able to look at our own ARP table and resolve it from IP to MAC, great. If we are not able to, that's where we end up doing an ARP request, which is basically a broadcast, trying to find out who it belongs to and whoever that IP belongs to, and normally say it's me, and here's my MAC address, and it would get, the response would come and it would be resolved. ICMP, Internet Control Message Protocol. With this protocol, it is a status and error messaging protocol. It does not move data. When we use commands like ping, or actually even trace route, trace RT, we are depending on ICMP. ICMP echo, request, and reply, they show with the ping utility. It has been a very useful tool. Unfortunately, ICMP is used by hackers. And what's presented here, it's allowed through most firewalls. I think that's changing. It kind of depends. I think with ICMP, we would probably allow it more internally. But I think when we start working out on the internet and trying to communicate through different vendors, through different companies we're trying to get to, if we decided to go and ping www.microsoft.com or CNN.com or whoever it happens to be that you want to try to ping, which is using ICMP, it would just depend on the destination on whether it's actually going to get through. So it's kind of hit and miss. I would say over the years, ICMP is being blocked more than it used to be. So yes, it is allowed through most internal firewalls, but I think we're seeing more of it being restricted more so outside, but it depends. So yeah, a hacker could send a redirect traffic by sending bogus ICMP messages to a router and, kind of throw off the whole communication through the ICMP. The management information base, that is something we see more with a protocol called Simple Network Management Protocol with management systems like Cisco Works and HP OpenView to monitor the status of routers and switches and servers and things we care about. DNS, Domain Name System, it is a hierarchical system. It does map the name of the computer, host names, to the IP address. We have DNS servers that hold resource records for a zone. It's called the authoritative DNS record for that zone. Call this domain name service. This can be enabled. Of course, it is enabled to a certain point on the PC to at least work with the DNS. Your workstations are generally not DNS servers. Your servers could be running the DNS service, the domain name service. It could be enabled on a variety of devices. Your home router is likely to have some of this built into it, as well as firewalling and so on. But we used to use a host file, and that had to be, you had to have every entry you wanted on every machine, and we kind of outgrew that a long time ago. So these days it is a hierarchical system with DNS, and our DNS server for our work would not have entries for Toshiba.com or HP.com or any of those. They would just have the information for their own, but yet know how to climb the tree, you could say. They know how to work their way up to like the .com or the .edu, and then work your way down to the proper first level, and then, like Microsoft, and then maybe beneath Microsoft, training.microsoft.com. Secure Shell. This was really kind of like Telnet, but meant to be more secure. So I think old timers sometimes still, they'll say the word Telnet, but they actually mean it has secure shell capability. So secure access to remote systems, and you basically use a secure shell tunnel, SSH tunnel. We would use this instead of Telnet and, the R utilities that you see in the Unix, Linux world. Server and client generate their own private public key pairs. We'll hear more of that in the cryptography chapter. Many times they will use a protocol called Diffie-Hellman for the key agreement, which is an asymmetric encryption. It carries out a handshake process, and they have to agree upon the parameters to actually set up this secure connection, the secure shell. So when you think of secure shell again, by the way, it uses port 22. Telnet used port 23. And it's kind of the way we do things now. What's really funny is if you go out there and look for Telnet client, you will actually find that most Telnet clients have secure shell, or even FTP clients will have secure shell capability built into it, like FileZilla or Secure CRT, and they all have like secure shell built into it. So again, secure shell uses public key cryptography, which is an asymmetric cryptography, and secure shell is used in functions like replacing telnet, replacing FTP, and that's what they're saying in this part of the slide. It says secure shell is typically used to log onto a remote machine, execute commands, that's replacing telnet, and transferring files. It's kind of like a secure FTP or a secure copy. So replacing what we normally do with traditional FTP. Remember, port 22, TCP port 22. And when you hear them say something like SSH daemon, that's like a process, and you hear that term more in the Linux, Unix world. So you would see this built into modern operating systems like the Mac operating system, Linux, FreeBSD, Solaris, OpenVMS, and so on. Just many different ones would have this. Even the Windows world, it's like almost a given. Secure shell you see in Cisco. Protocols, SNMP, Simple Network Management Protocol. This would be, again, my example of Cisco Works or HP OpenView, where you want to manage devices and you want to know if your server has had an issue, as maybe certain conditions are met, you want to be notified, like the processor utilization's too high for too long, or you're running out of hard disk space, you would like to be notified, or maybe an interface got shut down on your router or your switch, you want to know about it. This is all SNMP, Simple Network Management Protocol. And with that, it's like the master system is looking at the computers and systems of interest, and they're called agents. And they gather status information about the different devices. Again, the switches, the routers, the servers, anything of importance. And as far as this goes, there is a primitive security. We have public and private. Now, public, if we have public access, it's able to read the information on these devices called MIB, Management Information Base Data. It's kind of like a password of sorts. If we know private, then we could read and make changes to that data. Normally, you would not leave these default community strings, they call it, public and private, because that's kind of like an understood default. Then anyone could exploit, and get information with public and possibly make changes with private. Simple Mail Transfer Protocol, think email, port 25. This is something that would need to be secured, of course. Transmits mail between different mail servers. It's a protocol to send outgoing mail from the email clients. Many security books bring up a security concern where these systems are being used as a mail relay, an email relay. And email can be basically moved from one email server to another email server and passed on. And if it's not properly configured, you could find that your email server is being used to distribute spam, for example. So bad guys, hacker types, might look for systems that are not configured properly and then make use of those systems to distribute their spam. And if that gets done to you, you are now looked at as a system that is sending out spam. They don't want to communicate with you. They blacklist you. And you say, what happened? I didn't do anything. Well, you weren't paying attention, I guess, is the error here, as it wasn't really secured. Packet sniffers. You could think of a product such as Wireshark, used to be called Ethereal. Okay? And with packet sniffers, these are designed to intercept packets on the LAN, your local area network, that is. And you're just essentially looking at the traffic that's being communicated. There's hardware versions of this. You can do wireless. You can use just general software to do this, like the Wireshark I was mentioning. Sniffers can be used for your people to troubleshoot, so they're used in good ways, but they can also be used by hackers to see if you're not encrypting your information, and it could be plain as anything. They could see that. They could actually see that information, and when you run something like Wireshark, which you could freely download and run on your home network just to get proof of concept, you realize anything not encrypted is clear text. You can read it all. You can catch passwords and usernames. Like if you're doing FTP and it's not encrypted in any way, we can actually read all of it. Here's some packet sniffers. Wireshark is the big one. That's the one that it's been around for ages. It used to be called Ethereal. And it works in a variety of environments. Many books on Wireshark. The others are of slight interest. I mean, TCP dump is more raw looking. A WinDump is similar to TCP dump for Windows. There's an OmniPeak. Cain and Abel is known for a lot more than this. Cain and Abel would be a very interesting one to download and play with on your home network and not your work network. They would not appreciate that, and you'd probably get in a lot of trouble. Cain and Abel is known as a hacker tool. Your virus protection will probably think it is as well. It has great power. If you just go to their website and look at it, you can see that, but it can do sniffing as one of its functions. In this chapter, we have looked at the OSI model. We've looked at a variety of protocols. Look at the TCP/IP protocol suite, and you saw a couple of these: ICMP, UDP, ARP, DNS, Secure Shell.